In this video, we're going to discuss the free energy of a system, the Gibbs energy, and the cell potential, and how they are related. For a moment, let's think back to Gibbs energy. Remember that Gibbs energy was equal to the max work that a system could do. Most likely you'd never harness all of it, but it was the maximum that was possible, or it was the minimum work needed to be done in order to make an unspontaneous reaction occur. Well, how does this relate to our electrons? Well, imagine you have some cell system set up, and you have a flow of electrons, and it goes to something, and then here's your second cell. Well, what is that something? Let's zoom in here for a minute. We have electrons, and they're flowing, they're moving, they travel as they go from one side to the other. Well, an electron is a charged particle, and a moving charged particle exerts a magnetic field. Well, we can harness that. As electrons flow through our wire, we can shape it in ways, say a coil, and that coil can go around a system with some permanent magnets on it, and as the electrons flow, they'll create a magnetic field that will cause those other magnets to respond and could twist and say, maybe we've got a wheel on the end, and this is your Tesla, and you got a roadster here, and electrical current is driving our wheels. That's one way you can harness the movement of the electrons. Another might be you set it up through a piece of metal, you got some coils on one side, you have a different number of wrappings on the other, so you can change your voltage. Well, this can go to another type of material where maybe you're arcing electricity across because you want to make a plasma welder. Or maybe you could have this run through a heating filament, and it will give off light. Old tungsten bulbs. Things like that. There's various ways that we can utilize this flow of electrons, transfer it over to another piece of material, cause high resistance and therefore heat generation, make black body radiation, move other permanent magnets, all sorts of things we can do. We can do work. This flow of electrons can do work, which means our flow of electrons and our delta G have a relation. Well, they're not directly equal by any means. Our Gibbs energy is proportional to the negative E cell. Remember, we need a negative delta G to be spontaneous, but it's a positive voltage that is spontaneous. Well, the work max is going to be equal to the negative E cell times the charge. Remember that our potential is equal to 1 joule per 1 coulomb for every 1 volt. Our voltage is tied to the energy, and energy is tied to the work. How many coulombs are we moving at what voltage? That's going to tell us how many joules we can get out. Well, since for spontaneous reaction, the Gibbs energy is equal to the work max, we can set these equal. The Gibbs energy for our cell is going to be equal to the negative voltage potential times the charge that actually is moved. Now, that's important. How much charge do you actually move? If you only run the circuit for an instant, you get an instant of light or a tiny little bit of motion. Run it for longer, you get more light, more heat, or more motion. How much charge we actually flow through determines the amount of work we can get. Well, if that's the case, what's the charge? The total charge is going to be equal to the number of electrons that we actually move times the charge of electrons, and most likely per mole. This is chemistry. So what we really know is what's the charge of a mole of electrons. If we know the charge for 1 mole of electrons, we can say, well, I move this many electrons, so here's how much of a mole's worth of charge I have. We actually have this value, Faraday's constant, which is 96,485 coulombs per mole of electrons. That is how much charge a mole of electrons has. So we have a charge for a mole of electrons. Multiply that by the actual moles of electrons used, you'll find your actual charge. You'll be able to relate it back through our voltage to our free energy. Since remember that 1 volt is equal to 1 joule per coulomb, we can rearrange this a little bit and say that a coulomb is equal to 1 joule per volt, which we can substitute in here. So another form of our Faraday constant is 96,485 joules per volt per mole of electrons. Well, we said that our free energy, our Gibbs energy, was equal to the negative E cell times the charge. And the charge is the moles times the Faraday constant. What's the charge per mole times the number of moles of electrons? Bring this together a little more tightly. Negative NF E cell is going to be equal to the free energy. If we think about our units for a second, that's going to be mole of electron, 96,485 joules per volt per mole of electron, and volts. And so if we actually calculate it out, our moles of electrons will cancel, our volts will cancel. We'll be left in joules. So for any given voltage, the Gibbs energy is equal to the negative moles of electrons that we actually used times the Faraday constant times that voltage. If we want to put this into an example here, let's think back to our zinc copper cell. I got a cell, it's got a bar of zinc and some zinc solution. So there's zinc 2 plus and zinc solid. Goes through our device, whatever it might be. We got another bar over here, there's copper 2 plus and copper solid. Cu 2 plus 2 electrons go into Cu solid. If we look this up, E naught for this reaction, 0.34 volts. Zinc 2 plus 2 electrons go into zinc solid. E naught for that, negative 0.76 volts. The zinc has a lower potential, so it's going to get oxidized. The copper has the higher potential, it's going to get reduced. So we'd want to flip this around. Our zinc solid is going to break apart to become zinc 2 plus and 2 electrons, and those electrons will go into the copper. Well, flip the reaction, you flip the sign. Add this together, 0.34 volts plus 0.76 volts for 1.10 volts. Standard state says that this should be 1.10 volts. Assuming we start at the standard state and we give it just a little bit of time, and we add 1 gram of copper to solid. So a little bit of copper 2 plus ions start sticking to it. A little bit of our zinc ions start to break off from our zinc solid. And we don't let it get too far from standard state. So we're going to assume that we didn't really need to be concerned about our voltage changing much. But I've added a little bit of copper to my copper bar. Well, 1 gram of copper at 65.55 grams in 1 mole of copper. And for every 1 mole of copper that we made, we needed 2 electrons. We'll find that 0.0305 mole of electrons were transferred. So we started a standard voltaic cell. We ran it for just enough time for an extra gram of copper to accumulate on the copper side. That would have brought our 1 molar standard solution, if we had a liter of container, down to a little bit less than 1 molar. But our copper would be half that amount, so 0.985 molar. See, copper 2 plus would still be in solution. Close enough we can kind of pretend that we must still have our same starting voltage. Now I know the moles of electrons. How much work did I do in that time? What's the max work I could have done in that time? What was the free energy of transferring that many electrons? Well, our delta G is going to be equal to negative the moles, 0.0305 mole of electrons. Our Faraday constant, 96,485 joules per mole electrons per volt, and our voltage of 1.10 volts for difference in potentials of our zinc and our copper. Multiply those together, we will get out negative 3,230 joules. So for getting 1 gram of our copper-2 to plate out onto our copper solid, stealing electrons from the zinc, causing equivalent number of moles of the zincs to break off a zinc solid into solution. As those electrons flowed, the max energy we could harness from it was 3,230 joules. So 3.2 kilojoules for a pretty small number of moles. If you could maintain this voltage and crank it up to a full mole, we could figure out how much free energy we could get for that full mole of electrons transferring. If we did that, it'd be negative 1 mole of electrons, 96,485 joules per mole electrons per volt, 1.10 volts. In which case we would get negative 106,134 joules, or negative 106 kilojoules. Grand scheme of things, that's not a ton of energy. I mean, it's handy and it's useful and makes them light, but if you needed to constantly generate energy, you'd be using up tons of zinc and copper solids and zinc and copper ions. This is not a viable way to really run electronic devices, which is why batteries run out. Voltaic cells are pretty limited. They're honestly pretty dang wasteful. We've actually learned that. Most batteries these days are some kind of rechargeable battery, so that we don't have to constantly dispose of the physical material after every single usage. But we can calculate just how much energy we possibly could harness from the electron flow as these redox reactions occur, and in a properly built battery, you can maintain your voltage pretty much to the end. And so you have a reasonable idea just how much power you can get out of these batteries.